Okay. Okay. So like you would have known by now that whenever we are doing any kind of classification task, the first task is to express the like whatever observation you have. The first task is to represent that observation with the help of a feature vector, right? So now in general, a feature vector can be of like any any size, but let us say that we represent it by a d-dimensional vector. Now this vector, I mean, like it can be it need not exactly be a vector. It can be a scalar, it can be a matrix, and so on. But in like for the current analysis, let us just assume that it's a d-dimensional vector, and it can be, if necessary, it can be generalized to a higher dimension or lower dimension also. I mean, lower dimension is not really, it is just about setting d equal to 1, but instead of having a vector, it can become a matrix or something even more complex also. Let's not consider all those things as of now. So let us say, and you may, okay, and you must have also had some examples where the how good a classification is going to be depends on what kinds of features you are using, right? So mathematically speaking, we say that there is something which we call as the feature space. Let's call the denote it by this kind of a curly x, and there is a label space which we call denote by a curly y, and this and a classifier function is basically a mapping from the feature space x to the label space y. That means what? That means that like you take up any element from the feature space, which we can call consider as our feature vector. On that, we can apply whatever function it is, and the output is going to be some element in the label space, which we may call as a label. Okay. Now, now what exactly that feature space is, that depends on the user, depends on how the user chooses to represent uh, their observations. Okay, so suppose the task which we are dealing with is a very simple task of animal classification. That is, given a set of animals, or like you are given various animals and you have to classify them as which species they belong to. Okay, so there are various possibilities or various things can be used as features. So what you will choose as features may depend, like either you may be an expert of the domain by which you will come up with various features which you consider to be meaningful for classification of the animals, or you may, or what you may be is that you are like a big data person. So what you will do is you will put in all kinds of sensors, maybe a camera which can capture the picture of the animal, like a some kind of a device which can measure the weight of the animal, another device which can measure maybe the width of the animal, and some device which can capture the sound, the intensity of the sound which the animal produces, similar and various other things. And so like all those sensor outputs you will combine together to produce a really big data vector or feature vector and send it for the classification. Okay, so suppose like we have the technology to measure these few features: number of legs, number of tails, the color of the animal, the size of the animal, and its weight. Okay, so basically the animal is to be represented with a 5-dimensional feature vector. So basically for every animal, these 5 features will come. On the basis of it, the classification will be done. So the question might now arise that how exactly or what exactly will this function look like? Say like if it is a neural net, or okay, since you have studied KNN, so if it is a KNN, then of course what you will have to do is like you will already have a label training set. when a testing set comes in, a testing animal comes in, you will measure these 5 things of that test animal, compare all these things to the corresponding features of the different animals, and then we like suppose you and then like identify the k nearest neighbors, take a vote of the labels of their labels, and accordingly decide the label of the animal. If it is a neural network, then somehow we will have to represent it by this kind of a vector, and then you will have to send it through the neural network, like where there will be a series of operations that is multiplications by the edge weights and the application of the uh, this the activation function and so on. And then finally it will come to a softmax layer where we will do the uh, class probability classification, and that will give you the output. Similar things you will also do in case of, say, logistic regression. In case of in case of Naive or Bayesian classifier, you will build some kind of a probability distribution on the different features and so on, right? So basically, you will like calculate the probability of each the first feature having a particular value under a certain class. Okay, that is, if the class of the animal is, say, cat, then what is the probability that its first feature, namely the number of legs, is 3? These kinds of questions you will ask, right? And then you will have to measure this probability on the basis of relative frequencies in the database, and so like this answer will come to be 0. And similarly, for the other things also, you will like get the requisite probabilities. Then you will like multiply them, and on the basis of that, you will find which for which level the posterior probability is the maximum. So all these things are there. Now the point to be noted here is that, so these are the 5 features which are being provided to you. Now it may be the case that some of these features may be redundant. It may also be the case that these features are not enough. Some more features may be needed. Okay, so like if it is like given these 5 features, do you think some of these features can be redundant? That is, even if we drop those features, it would not make any difference. What is your impression? Do you think all these 5 features are really crucial for the task of animal classification? Or suppose the classification problem is simply cat versus dog.
Number of legs are not needed.
Yes.
Okay, and why is that the
So
case?
tail also for dog and cat.
Yeah, right. So why do you think so? Why are legs and tails not needed?
Because both are same
So
for both.
because both have 4.
Right. So it's like saying that in both the classes, the distribution of this feature is pretty much the same. In fact, not only is the distribution same, its value is actually constant in both classes. Right. So that way, both of these are not really very like basically they are not useful. So if they, why do I say they are not useful? Because because I want, what I really want is such features which will be able to distinguish between the different classes. I do not want to describe a cat or describe a dog. What I want to do is I want to draw a separation. I want to create a decision boundary that here, up till here, cat will be cats, up till there it will be dogs. But in case of these 2 features, no such decision boundary even exists, because both cats and both classes are like, there is no no decision to be made on these two features. So we say that it's like they are redundant features. What about color? Like say for do you think the feature of color is useful or useless?
Sir, it is not that useful in case of differentiating between cats and dogs.
Correct. Because like that is, it's unlike legs or tails which are constant. It is not that that all cats and all dogs have the same color, but roughly they take value. Each cat or each dog takes their color is basically from the same set. That is, it's like yellow, white, brown. These are the common colors for both cats and dogs. That is, it's not that you there are some red cats and some blue dogs, or some green cats and or some pink dogs. It's not like that. So color may not be as useless as it. So it's possible that white dogs are a bit more common than white cats, or brown cats may be a bit more common than say brown dogs and things like that. But like those are marginal differences. So the decision boundary is not that prominent in case of this color. So we can say that this is a rather weak feature. On the other hand, about size and weight, like these probably are much clearer differentiators. That is, we all know that a cat is much smaller compared to a dog, and by the same logic, the dog is also much heavier than a cat. So, in as far as these features are concerned, we we may think that a very clear decision boundary exists. But then we may also understand that these two features, in a sense, are correlated. That is, if some features, that is, if an example's size is high, most likely its weight will also be proportionally high. Yeah, and if it's similarly, if some examples size is small, its weight will also be proportionally small. So having, I mean, the proportionality constant may not be, or the proportionality may not be exactly constant for both cats and dogs. It's possible that in one case the density is higher than the other and things like that. But still, we can say roughly that size and weight are roughly correlated. That correlation coefficient may not be 1, but it will definitely be quite high. So we may not, if we are, both are these features are useful, but it may not be very useful to have both of them together. One of them may be enough. Okay, so basically the punchline is some of these features are more useful than others for classification. But again, it depends on what are the classes. So for example, if I am doing a human versus snake classification, then the number of legs, number of tails will be definitely be useful features, right? So uh, so which features we cannot always say that these features are not important. Which features are important, which are not, that will depend on the exact context, the specific problem which we are trying to address. Ultimately, it boils down to whether we can use a particular feature to define a clear decision boundary between the classes. Okay. And sometimes, like, you may be provided with hundreds of features, but out of that only a small number of features may actually be enough for classification. The other features may be useless either because the decision boundary does not exist, or because the decision boundary is not pronounced, or like I mean they are all pretty much correlated. Okay, so what we are now going to do is we are trying, with the help of some examples, we will try to quantify this matter. So let us come to another problem with which we are all familiar with. So this is related to recommendation, and that is so like when we use some kind of a recommend these retail engines like Amazon, Flipkart, and so many other things where from which we can buy some products or avail some services, and based on which we can give some feedback, right? So suppose a person has purchased this camera and has given some feedback out of 5. So let us say 4 out of 5 they have given. So now the question might arise that why did they give this feedback? Why did they give 4 out of 5? So probably the answer is that that person focused on different features of this product, and they mentally gave some kind of ratings to each of those features. I mean, they may not have actually written down the exact ratings of each and every feature separately, but like intuitively they have some idea about what are the features they are interested in, and whether they are satisfied with those features or not. And it will also there is also this notion of importance of the different features. For example, this camera, this may be excellent for shooting videos. It may give like a very high frame rate, but it may happen that as an user, I am not interested in taking videos. I only want to take high quality images, static images. So in that case, whether the video rate is like 5 frames per second or 80 frames per second, it will not make any difference to me. I simply don't care about it. So like it may be that despite having a very good frame rate, the picture resolution is not that great. So I gave, like did not give it full 5 ratings. I gave it only 4. Or there may be some other reasons also. Or it may simply be that I just have like this belongs to the brand of Canon, and I have uh, some bias towards this towards or against this brand. So I give it uh, 4 out of 5 just based on brand. Or it may be a complex combination of various factors. It's possible that I want high resolution cameras, but I also want them cheap. So that is I may prefer a 20 megapixel camera, but if it is like if it costs me some 12,000 rupees, then I don't want it. Rather, I would go for a 10 megapixel camera which costs 5,000 rupees. So this kind of there may be a complex interplay between different features also when I am giving the rating. But the problem is that these features are to the different the ratings to the different features are not revealed. They are not known. And even even I myself may not know what exactly are the different features I am looking for and what rating I am giving to each of the features, right? So if I now have to so if I am a search, if I want to run a search engine which wants to recommend more cameras to the user who has already purchased various cameras, then of course I will want to suggest more cameras which the user will like. So for example, for that purpose, of course, I will need to know what are the aspects of the camera which the user likes, right? So but that information, let us say I do not have. So what will I do? So I will have to dig into the data. I will have to look into the data of what cameras the user has purchased so far and what ratings they have given so far. So from that, my task will be to elicit the information about which features may be useful for that user. So let us say that this is the rating history, camera rating history of our user. So this user, she has purchased 8 cameras so far. And you can see that for each of the cameras, we have marked the company. Let's say there are 2 companies. We have also marked the colors, are they black camera or white camera? The pixel resolution, they have been marked, video frame rate marked, price marked, and her ratings also marked. Okay. So from now, like there is in 7 cases the rating is known. In the last case the rating is not known. It has to be predicted. So as I said, if I have to predict this rating, then I will have to understand which of the features are important to the user. Okay. So offhand, just by looking at this data, can you can any of you make any observations about which features might be useful for the user and things like that? For example, yeah. Anyone wants to reply?
Sir, it looks like a video rate.
Video rate, okay. And why do you think so?
So because like she has given 5 stars to 50 FPS in spite of the price, like it's the highest price, so price doesn't play a role, much of a role here. And even the resolution, it doesn't go as per uh, for example, she has given 3 to 20 MP resolution.
Okay.
And also the color doesn't matter to her because like it is not like determining what she is giving the rating.
How do you know that it is not determining, or how did you make out?
Because like even for the same company, she has given like same rating to both black and white.
Right. So yeah, so you are thinking along the right tracks. So let us do one thing. Let us go one by one. So let us consider each of the features one by one. So let us say that okay, first of all, let us forget all the features and see what is the basic. Okay, let us move to a different, slightly bigger form of this data set. So let us say that this customer, she has rated 100 cameras. I mean, this you can assume that is some kind of a snapshot of this data set. So let us say that she has rated 100 cameras so far. So now, first of all, let us forget all features and let us think that just based on the numbers, can we only the rating numbers, can we say something? I mean, there are some people who have a tendency who are like very polarized in their opinions. That is, either they will give 5 star or they will give 1 star. So is this that kind of a person, or is this a more nuanced kind of a person who will give like different ratings like depending on their level of satisfaction? So if you look at that, the counts of the different ratings, you will see that they are actually roughly comparable. That is, in 17 cases she has given 5 stars, in 20 cases she has given 4 stars, in 18 cases 3 stars, and so on. So you can see that it is like if it had been fully uniform, then each of them would have, of course, have gotten equal ratings. So it would have been 20 each. It's not 20 each, but it's nearly 20 each. So we cannot really say anything about her inherent rating bias. No such bias seems to exist. Okay, so there is no information is to be gained from here. Now let us consider the feature of company. Okay, so there are, again, let us say that we have two companies, C1 and C2. Okay, so in C1, and out of the 100 cameras which she has purchased, you can see that 54 are from company C1 and 46 are from company C2. So now let us see that the ratings in both the cases, and as you can understand easily, that in case of company C1, she is usually giving low ratings more commonly, 15, 18, 10. So if we let us say for now that 1, 2 rating, 3 ratings I will consider as low, 5 and 4 I will consider as high. Okay, so I am just for the time being binarizing my data set. So so we can say that the low features, the frequency of the low features is 43 out of 54. And the frequency of the high features is only 11 out of 54. Okay, so so in her rating, company C1 seems to be faring really badly. That is, there is only 11 by 54 probability that she will be giving this good feedback to them. On the other hand, if we see company C2, we can see in 20 cases she has given low rating, but in 26 cases she has given high ratings. So in this case, her probability of giving a high rating to company cameras from company C2 seems to be considerably larger. That is more than 50%. Certainly more than 11 by 54. So here it was just about 0.2%. In this case, it is like well above 50%. Okay. So on the basis of this, can we, so in this case, clearly the difference between the two companies is large, but so can we say that she is actually giving the ratings based on company bias? What do you think? Do you think she is like biased against company C1 and biased towards company C2 and that is driving her ratings?
Yes, maybe can say that because there is a difference how she is preferring company C2 over
Okay.
C1.
Okay, fine. Anyone
Sir,
else has?
may not be the case because inherently company C1 is producing cameras which are not suited for her.
Yes, right. So both answers may be right. It's possible that a user has certain bias towards some company. Yeah, if someone is answering, please unmute and say. Yeah, so it may happen that she has some bias against company C1 and some bias in favor of company C2. That is also possible. It is also possible that like some of the ratings, there some it may really be some other feature which is important for her, but for whatever reasons company C1 does not produce that feature and company C2 produces that feature. Like as like in this case, some of you pointed out that it seems the video rate is important, seems to be important for her. So it's possible that camera C2 is a specialist in video cameras, while camera C1 is a specialist in static cameras. So we cannot really, so in that case, naturally her ratings will be biased against company C1 and in favor of company C2, not because she has anything for or against these companies, but like these company, one company gives her what she wants, the other company does not give her. That's all. Right. So we cannot, so basically that means we cannot really stop our investigation at this stage. It's possible that company C1 will also manufacture some other good video camera which she will give high ratings. On the other hand, it's also possible that company C2 will produce some other camera which she will not like. Right? So we have to probe further. If we consider the color feature, I mean, it's not very rational, but some people may have some bias towards one color of cameras. So you can see that, but that does clearly is not the case here. So there are 70 black cameras and 30 white cameras. So if you see the distribution of the ratings in this case, so we have decided to binarize it. So we can say this is 48, this is 22. So the probability of high rating among black cameras is 22 by 70. Among white cameras, it is 15 by 30, right? So actually, so in this case, this one is 50%. This seems to be definitely only 30%, right? So it's possible that there may be a slight bias for her towards white cameras. Right? So some difference, I mean, some difference is definitely there. So that's another feature. So this way we can like keep counting the different features one after another. For each feature, we can actually look at the distribution of the different ratings. And C, what we are basically doing is there is a base distribution over the ratings, which is this distribution. So in this case, like we can see that this is 37, this is 63. That means overall there is 37% chance of giving a high rating. Now, if I for a particular camera, if I want to predict whether she wants to give a high rating or she may give a high rating or a low rating to it, what we really want is for each feature we want to understand, does this feature significantly alter her rating behavior or not? How do I know whether it alters her rating behavior or not? So in this, like if you consider this company feature, it seems that in one class, if this feature takes one particular value C1, right? So like we can say that this feature is basically dividing all the training examples into two groups or into two clusters, if we call it. One is cluster 1, for which C equal to 1, and the other is cluster 2, for which C is equal to 2. Now the question is, as a result of this kind of clustering, did her rating behavior change? And it does seem, yes, it did change. For the in one case, the probability of high rating went down from 0.37 to 0.2. In the other case, it went up from 0.37 to 0.55. Right? So we can say yes, on the basis of this feature, it did affect her rating behavior. If we consider the color feature also, we can see that in one case from 0.37 it went up to 0.5. In the other case it went down from 0.37 to 0.3. Okay, so like if you compare these two things, one thing becomes clearer, that in both cases it seems there has been a change in her rating behavior, but this change is more prominent in for company and less prominent for color. Okay, so between these two features, it seems that company is making a bigger difference than color. Of course, that does not mean that we can just use company as a feature, as some of you correctly pointed out. It's possible that company is basically a proxy for some other features. So we can these kind of analysis we can do for the other features. So basically what I am hinting here is that some features are discriminative. What is discriminative? As in the cat dog case also, what I was telling is that I want such a feature which helps to create a decision boundary between the two classes. That is, on the basis of it, you can identify some kind of threshold such that if any example lies on this side of the threshold, the label will be something with high probability. If it lies on the other side of the threshold, the label will be something else with high probability. Okay, and for company C1, like this is what we have seen, that if the company is C1, there are total 54 examples. And the distribution of the two classes, low rating and high rating, among them is 4311. In case of company C2, it is 2026. Overall, it is 6337. Okay. Now, just a second. Now if we consider price as the feature, so price, if you see, price is like it's something that unlike company and color, which have only two values. Company has C1, C2, C3, sorry, only two values, C1 and C2. Color has only two values, black and white. But if you see price can take many values, 200, 250, 300, 400, 500, 350, so many prices we are seeing. out of only 8 cameras. Mind that this is only a snapshot of the dataset. The full dataset has 100 cameras. So there may well be almost 100 different prices. Maybe only a small number of repetitions might be there. So now does it mean that for each of the price values we have to like calculate this kind of distribution of the feature, I mean of the ratings? That will be a very cumbersome task. And in any case, the number of examples we have for each of the single or unique price values will also be very small. Maybe only two or three or four cameras will have the same price. Most of them will have different prices. So it's not very useful in this case to consider the individual values of the prices. Rather, we have to set some kind of threshold. So that is, in other words, we have to come that is close to somehow binarizing the price feature. Now, whether you exactly, that is whether you binarize it, making it, dividing it into two groups, or maybe make it into 3 groups or 4 groups, that does not, that is like ultimately your choice. But whatever it is, your aim will be to reduce it to only a small number of possible values. Okay, and suppose you decide to binarize it, that is less than something and greater than something, then what that something is it 300 or is it 400 or is it 500? That also is ultimately your choice. In some cases or in some situations, there may be some intuition for it to for you to choose a particular threshold. In other cases, no particular intuition may be useful. So one thing which you can always do is to use the median value. So median value of a feature, you know, I'm sure you know what is meant by a median value. Median value basically means like 50% will be less than that value and the other 50% will be more than that value. So if like, so you, one possibility might be to choose the median as the threshold. But that's not the only possibility. There might arise some situations where a different threshold might be chosen, right? So basically, so suppose you are choosing this threshold. So in this case, what you have done is, or what you observe is, there are 70 cameras which cost less than 70, sorry, less than 300. 25 of them have got high ratings, which means slightly, say about 35%, 0.35. Okay. On the other hand, if you see the cameras which are more costly, there are 30 of them and they have got 12 of them have got positive ratings, which means about 40%. Okay. So while the overall behavior is 37, if you do not consider any feature, it's 37%. So that way, so this shows that like price does not say, like at least for this particular threshold for 300, there does not seem to be any significant change in the rating behavior. It's not that uh, uh, she has any particular liking or disliking for cheap cameras, nor is it the case for expensive cameras. Okay, so before discarding the feature, let us maybe consider another value of the threshold. Instead of 300, let us consider 500. Okay. So there are 500. There are 90 cameras, right? Full 90 out of 100 cameras which cost less than $500. And if you see those cameras, out of them 35 are positively rated. So 35 by 90 comes to close to 0.4. Correct? If you consider the more expensive cameras which cost more than 500, there are only 10 of them and only 2 of them, that is 20%, have got high ratings. So like if you consider the base case high rating 37%, from 37% in this case is a slight marginal increase to 40%, but in this case there is a significant drop to 20%. So it's like saying that if a camera is costs less than $500, there is not much we can say about it. But if it costs more than $500, we are more or less convinced that she is not going to like it. Right? That's what it suggests. But there is again a catch here. The catch is that this data set is not at all balanced. One has 90 entries, the other has 10 entries. Right? So only out of 10% of the entries, we cannot really give much importance to what we have seen so far. That is here out of these 10 entries, it's like 8 examples are like they have got low ratings and 2 examples have got high ratings. That difference seems to be quite large, but after all, there are only 10 such examples. If you had given me this kind of thing had been observed over say 30 or 40 examples, then I could have believed this, but with such a small number of examples, this seems to be a bit on shaky ground. Okay. So what does it bring us? So we investigated several features one by one. So in fact for the price features, we considered 2 different thresholds. So which are discriminative and which are not. So and what do I mean by discriminative? Again, basically I'm talking about the decision boundary. So for company feature, there are 2 possible values, C1 and C2. If company is C1, what's the probability of high rating? Very low, 0.2. If company is C2, what's the probability of high ratings? Quite high, 0.55. So this is, so if we choose company as a feature, it becomes relatively easy to decide. If basically the rule becomes, suppose a new camera comes. It's a new camera. So then what will I do? I can simply consider its company feature. If the company is C1, I can say with with a lot of confidence. I mean, not 100% confidence, but 80% confidence that she is going to dislike it. Okay. Why only 80% confidence? Because there are 20% cases which have company C1, but she still has given them good ratings. So, so the rule which I have made, which I am trying to suggest here, that get a new camera, look at its company. If the feature is C1, then predict low ratings. If the company is C2, then give high ratings. This is the rule which I am trying to predict. Which I am trying to suggest. Okay. So if if this is the case, if the company does turn out to be C1, I can predict that its rating will be low with 80% confidence. On the other hand, if the company is C2, then I can predict that its rating is going to be high with how much confidence? Yes.
0.55.
55%.
5%.
Yeah, 55%. And why is it so? Because out of the 46 examples, out of the different examples which I have seen so far, it seems that like in those which belong to company C2, there is 55% of them have got high ratings. So I am declaring the rating to be high because it is for 55% are getting high rating, 45% are getting low ratings. So there exists a significant difference between them. So I can decide that in this case I will decide high rating, but the difference is not much. Okay. So we can say that, okay, on the basis of this, we can come up with a classification rule, like simple classification rule like this. But if you consider this feature, whether the price is less than $300 or more than $300, so we can see that in both cases, the probability of high rating is pretty much the same. So there is no difference to be made in this matter. If you consider the like this feature, whether the price is less than $500 or higher, in one case, you see that there is 40% chance of giving high ratings. In the other case, it is 20% chance of giving low ratings. So ideally that means that if you see a camera that costs more than $500, you can say with 80% confidence that it will get low ratings. However, there is a catch. The catch is that there are too few samples. The problem is not with this number, but rather with this number. There are only whatever the rule which you are formulating here is on the basis of only 10 examples. In this case, you have done it on the basis of 54 and 46 examples, but in this case, you are making a rule on the basis of 10 examples, which is not a great idea. Okay. So basically, you can say that it's an evaluation of the different features. So now, based on this, we can say that the first one is a good feature based on which it is possible to make a reasonable classification. The second one, whether the price is less than or $300 or more than $300 is a bad feature. On the basis of it, you cannot make any classification. And the last one, whether it's less than $500 or more than $500. Yes.
Sir, in the price less than 300 feature, like even that is also not balanced, right? So how are we saying that it is a bad feature?
I mean, it's not balanced definitely, but even I mean, it's like that is then also we are okay. If you forget this part, if you see this part, then we are saying that it's 0.36, right? Which is very similar to 0.37. So, here, despite having so many examples, we are not like it seems to be useless. And this one, if you are like it, of course, it depends on whether 30 you consider to be enough or not. If we consider it to be not enough, then obviously on the basis of that, we cannot say anything about it. Or if we consider, even if you consider it to be enough, then also the like it's 0.4, which is very close to 0.37. So either way, it's a bad feature. Whether you it not so much because of this one, but more because of this one. But if you consider this one, this is not very useful anyway. This part of the segment is not very useful. It's anyway giving me 0.4. So based on this, I would have called it as a bad feature. Based on this part, I am tempted to call it a partially good feature, but with a caveat. Okay, so we can say it's a doubtful feature. So then the question is, like, what do you mean? So the idea is basically you have to identify the most discriminative feature and use it to classify. So the classification algorithm which I am trying to suggest here will basically do as follows. It will take any example. It will focus on one feature. It will consider its value, and based on that value, it will predict a level. So, that's the, let us say that is the algorithmic framework in which I am going to operate. Choose a feature, check its value, predict label according to a simple rule. According to this value. This is the basic algorithm on which I am going to do the classification. This is what it will look like. And this I am calling as a decision stump. Okay. Decision stump. So now tell me, on the basis of what we saw, what kind of so if this is the way you want to do the classification, then what kind of feature will you be looking for? right? So like I have already given you like these three examples. I have also already said that this is a good feature, this is a like a bad feature, and this is a like a doubtful feature. So on the basis of this, how do you character given that I have to like do the classification according to this framework, what do you think the best feature should look like? Or which feature is or what is the criteria for a feature to be called as good? What is your opinion? Quick. What is your opinion? What feature will be good?
So you're asking in general way or in this situation which feature is?
Not out of these three features, but like in general, what do you think is a on the or on the basis of these examples, what do you think? What is a general idea of a good feature?
Good feature is which helps us to easily decide and which also has enough number of examples in it so that it's not very
The
doubtful.
the second one I agree. What the first one you need to explain a bit more. Why it how it easy how any feature easily helps you to understand.
So like means there should be a significant difference also, like uh, to make a measure, like we are taking two cases here, so the both the cases should not be like having similar probability. There the probability of
Uh,
choosing ones
yeah,
should be a significant different than the other.
right. Right. So, or the same thing you could have said in a slightly different way also. You could have said what that is as like when I want to predict, that is suppose I have like for on the basis of any feature I have divided into like divided the entire set into two groups. Okay, two clusters. Like these examples have one value of the feature, these value have the other value of the feature, and on the basis of and for this one I like if any example comes in this cluster I want to assign it a probability like a label, and if it comes in this cluster I want to classify assign it a different label. Okay, so the thing is that so I is so like so the so one is that the probability of one label of any particular label should as you mentioned should be significantly different in the two cases. It's like saying that label high in this case has only 0.2% probability, and in here it has 0.55% probability. So that's a we can say is a big difference. You can look at it in a slightly okay. So this is the case. Now suppose from point 2 I can bring it down to point 1, and this 0.55 I can bring it up to 0.75 for a different feature. Okay, so suppose instead of company I let us say some other feature X I use which has compare two values x1 and x2. In one case the probability of high ratings is goes down to 0.1. In this case the probability of high rating goes up to 0.75. So as you said, the difference should be quite high. So in this case, the difference has gone definitely become higher. So you should definitely prefer this feature. Correct? That is, this feature seems to be more useful than company. But that's definitely true. But apart from the fact that in this case, point x1 and sorry, point 1, the difference between these two things is the difference between these two probabilities is high. What else do you notice about these probabilities? What about this now? Like forget the difference. That is, forget the difference between point 1 and 0.75. But what about this number point 1 itself? It's a low number. That means what? That means almost, yeah.
Close to extremes.
Yeah, close to extremes. That means what? That means almost all the examples here belong to the one class, namely low. And here almost all the examples, 75 of them belong to one class, namely high. That means what? That means, as you said, close to extremes, which basically means that pretty much all examples of this group belongs to a certain class, and pretty much all the examples of this group belongs to a different class, right? So so in other words, it's like these two are fairly homogeneous classes now, homogeneous clusters now. So what is the so why is that important? Why do I like whether it's homogeneous or heterogeneous? How does it matter?
The more homogeneous it is, the more easily we can separate it.
Exactly. So suppose one new camera comes into this cluster. So I will have to predict based on that I will have to predict its class level. So if it is homogeneous, if this cluster I know is homogeneous, then it will I can say that since it is like this value is like the values of the other ones, so I can say with high confidence that its level will also be the same. Basically using the nearest neighbor logic in this case, right? But if it is a heterogeneous one, then I cannot say something so easily. Then I will understand that there are several examples with this with this level also, and several examples with that level also. So even if one level may be in the majority, it's not that the other level does not exist. So I cannot. So I can never be very confident about my classification. But if it is a homogeneous cluster where 95% or 99% have the same level, then I am more or less convinced that I can confidently classify this example. Okay, so since it's 12 and I like you may have other classes and I also have other class. So I will stop now and we'll discuss this tomorrow at 8 a.m. Okay, thank you everyone.